Yeah, good morning. My name is McManus and I'm a civil engineer with ESB International, and I'm going to speak to you this morning about how we implement some of the BIM processes into our design, our civil design on wind farms. So, what is BIM in civil engineering? Building and information modelling is a well-established process that John has just spoken to you about. But does BIM apply to civil engineers? Can I use BIM if I don't have it built? Well, the answer is yes, and while it seems to be somewhat behind the world of BIM for structural engineering, it is highly relevant for civil engineers and will only continue to grow in importance. BIM is not just about civil 3D, although the term model-based design is used quite often when applying BIM processes to civil engineering. And to understand how BIM applies to civil engineering, we only need to look at the design process for, in our case, a wind farm. So at planning stage, for our civil infrastructure on a wind farm, this is where we have the greatest ability to influence the project. And Autodesk Civil 3D is an excellent planning tool, as it allows us to quickly evaluate the proposed project and generate suitable alternatives. Then at detailed design stage, we can build an intelligent 3D model of the wind farm infrastructure, roads, hard standings, compounds, drainage, etc. And during construction, data from the models can be transferred to construction drawings relatively easily, and our deliverables not only include our 2D drawings, but also the model itself, which can be a very useful tool for the contractor on site for generating 3D setting out data and volumes, etc. So, the starting point when we're creating our BIM model for our wind farm is to model existing ground conditions. This information can come in many forms and can be collated within Civil 3D. Typically, we receive topographical information through LiDAR. Once we have our ground model, we can identify any gaps in the information, and then we can go out and do GPS surveys or drone surveys. So we just have an example here. Colin spoke to you about a drone survey he did on one of our upcoming wind farm projects in Grousemount in Kerry. And we're widening a lane for access into the wind farm. And Colin did a drone survey which produced a detailed aerial image and contours of the area, which allowed us to overlay our design on top of it, finalise our design, and work out the relevant quantities. You just see the design overlaid there. A huge part of what we use Civil 3D for wind farm design has to do with peat stability and peat excavations. It is incredibly important to factor in peat into our 3D model prior to our design. Once a greenfield site is presented to us for assessment, the overall goal is to obtain as much ground investigation data to inform the site design such that access roads are located to minimise peat excavations, etc. At planning stage for a wind farm, we typically carry out a probing on site of a 100-metre grid. And in Civil 3D, we can then create a peat depth map, splitting the site up into areas of deep peat and shallow peat. We also use these peat depths to create our bottom of peat surface, which we can use for volume calculations further down the line. We can also create a ground slope map, which just splits the site up into areas of different slopes. And then we can use a combination of Civil 3D and Autodesk mapping tools to create a peat stability index map from the ground surface, the peat depth surface, and assumed peat strengths. Peat stability index map is a coloured map which splits the site up into areas of low risk, medium risk, and high risk categories. And once we have this, we can visually inspect the site to get a feel for areas of site to avoid, thus enabling us to site the roads properly. It's just an example of an area where the layout of a wind farm is optimized to avoid an area of deep peat. So once we've decided on our locations for our roads and the wind farm, we can then begin to build our 3D model. And we use AutoCAD Civil 3D to build this. Civil 3D is an engineering design and documentation solution. We begin by creating alignments, which are effectively the center lines of all our roads throughout the site. Doing this will refine the layout as we can incorporate the turbine supplier's requirements into horizontal alignments and turning areas into the design. Once this is established, we create a profile through which these alignments, through which we can create our design profile, which will also incorporate turbine supplier requirements for vertical alignments. We can then lock the profile to the alignment, which means that further down the line, if any modifications are required to the alignments, the level data associated with that particular location on the alignment is fixed and that will not be altered. The alignment and profile functionality is at the core of what makes Civil 3D such a great tool for us. They are our single source of data. And changes made to an alignment will also change the profile, its labeling, any volume calculations or design that is done from using it. Our model is the primary location for our alignments and profiles, and using a combination of data references and XREFs, we can share our data to other designers, which avoids data duplication. But once we have our alignments and profiles, we can create our assembly, which is effectively what we want the road to do. So the assembly contains a lot of information within it. It contains the build-up of the road, the batters at which we want the edge of the road to go down to. We can choose what surfaces we want the batters to go to. If we have bottom of peat information, top of rock information, we can also build in other elements such as berms, fences, cut-off drains, etc. This assembly would typically be refined through detailed design phase in order to build in as much information into it as possible. And once we have our assembly, we can push it through our alignments and create our construction corridor. It's just an example of a hard standing with the cut and fill associated. It's a simple graphical form. It's just a corridor of a complex junction on one of the sites, and just a 3D rendering of the same junction. That's just once the design is finished, you just get a 3D design of all your infrastructure on the wind farm. So, just to give you an idea of the scale we're looking at, that blade on this vehicle there is 57.2 meters long. So once we have our model finalized, we then use sweat path analysis in order to make sure that our design will accommodate these vehicles and be able to successfully deliver these blades to site. It's just a fairly basic example of a blade, a 57.2 meter blade coming around a turn up onto a hard standing. You see the turbine foundation and the turbine and the cut and fill on the hard standing. And this allows us to produce drawings then which show in red the wheelbase of the vehicle, in green the body oversail of the vehicle, and in magenta the blade oversail of the vehicle. So once the model has been created, we then use it to extract relevant quantities. Controlled handling and deposition of our excess peat is a critical part of what we do. it's essential to accurately quantify the excavated peat volumes in order to reduce any risk. We use Civil 3D to calculate these quantities. So once we have our full model from the site, we can go back to our peat stability index maps in order to cite any locations for repositories or mineral soil storage areas, which we can then model in Civil 3D in order to ensure they have the capacity to store all the quantities that we're looking at. So that's just a simple example of a borrow pit repository, which we excavate material to use in the construction of the wind farm, and then we can use it to store material afterwards. So now that we have a model which was generated at a preliminary design stage and modified and refined during detailed design, we can extract information from the model to be used in construction. We can create plans, long sections and cross sections which are dynamically linked to the model, and generate setting out reports of the various elements of the model. As the project is being constructed, we can take back as-built information and we can input these into the model in order to establish that it's been constructed as per design. We can also use it to identify any areas which might pose problems in the delivery of the blades to the site. We can do a level comparison and identify any areas which might pose problems for vertical alignments for the turbine delivery vehicles. So Civil 3D is not really whilst it's a 3D modelling tool, it's not necessarily a 3D visualization tool. So there are certain elements of visuals that you can see. That's just a fairly simple model of our Grousemount wind farm in County Kerry, which is the zoomed in version. And this is just a simple video of, you can see the cut on the left and the fill on the right hand side, which are cut off drain above it. You can also see the build up of our road there, which are capping a layer, and our general fill. You can see our turbines coming into view there over the hill. So it's just a fairly simple showing of what it's going to look like. Just let it go. Just see us coming up onto the hard standing, and you can see the cut and fill and the hard standing and the turbine foundation there. Again, this is just a short video which was used in order to visualize a hard standing on one of our wind farms, which was going to be a significant amount of fill going in. So it was just to get a picture of what it was going to look like, and how it was going to be built, what were the dangers. You can see the piles going in there. This was just a slightly unusual case, and it was just used as a visualization tool in order to establish what it was going to look like. See the foundation going on there. And some backfill. And that's it for my presentation this morning. I hope you're given some idea of the way in which we incorporate BIM processes into our design for wind farms. Thank you.
Thanks, Liam. Thank you.